Good afternoon, everyone. Welcome to the press conference on the latest results from the ESA Rosetta mission. And I would like to remind everyone that we'll open the floor for questions following short presentations from the speakers. And we'll start with Matthew Taylor, who is the Rosetta project scientist at the European Space Agency, or ESA. Then we'll have Hans Ulrich Auster, who is the principal investigator for ROMAP, the Rosetta magnetometer and plasma monitor on board Philae, and he's at the Technische Universität Braunschweig in Germany. Then we'll follow with Karl-Heinz Glasmayer, who is the principal investigator of the RPC-MAG, the Fluxgate magnetometer in the Rosetta Plasma Consortium, and he's also at the same university in Germany. And then we'll have Stefan Ulamek, who is the Philae project manager, and he's based at the DLR, the German Aerospace Center. Well, now, Matt, you can start.
Thank you, everyone. Okay, I'm Matt Taylor. If you didn't know, I'm the ESA project scientist. I'll give a brief overview, very brief, of where we are at the moment with the mission. If it has escaped your notice, we are now around a comet, around CG67P. We've got little medals down the front here of it. We have been since August last year. We have been in orbit, but now we left orbit recently at the end of January. We had gravitationally bound orbits, then we went into these quite extravagant trajectories to do flybys. We had one in Valentine's Day, where we reached about 6 kilometers from the surface and were able to image very close to the surface. We have a close flyby at this radius and actually managed to capture the shadow of the orbiter on the surface of the comet. Subsequently, we were doing other maneuvers to go far away from the comet and then come back in again. And in March, we did another flyby, but had started to, and in the previous flyby, we'd experienced some issues with star trackers. And then for the March flyby, at the end of March, which is graphically represented here, where we were flying over roughly the neck region, we were having some problems with pointing, where the star tracker navigation was getting confused because of the cometary environment. So we had problems with pointing, we had a safe mode, and because it's safe, what the spacecraft does is fly away from where the danger is. This is what would happen in any circumstances. Even if the comet split as well, this would be another thing we'd do. We'd move away, very far away from the comet, and this is what happened. This is a navigation camera image. I think this is around over 300 kilometers away. So that's what makes you safe. You get away from where the danger is, which is actually the comet. Now we are undergoing a bunch of pyramid-like orbits to reapproach the comet. This is similar to the trajectories that we had last year, in the second half of last year. We'll alternate these with Terminator orbit as well, so we'll go into the plane of the Terminator to get a feel for how the spacecraft is doing around the comet, because it turns out that it's actually quite difficult to fly spacecraft around a comet. Today, you'll hear about the first results actually from the lander, but more importantly for me is that we're seeing combined measurements from both the orbiter and the lander. I think that's fantastic. This is a great achievement of the teams. This is going to give us a fascinating insight into the primordial solar system. We'll also hear a little bit about Philae's journey across 67P following the touchdown on the 12th of November. This is a cartoon, not a real image. And also from dear Stefan, we'll have an update from the lander itself. And with that, I will pass over to my esteemed colleagues.
Yeah, my name is Hans-Ulrich Auster. I'm working at the Technical University in Braunschweig, and I'm the PI of the orbiter of the lander magnetometer experiment. And what we did, we tried during the descent phase to measure the magnetization of the comet. And this is shown here. First of all, we are the only team probably which is benefiting from these jumping of Philae, because usually we only had the chance for measuring at one place the magnetization. Now, after all these bouncing periods, we are able to measure the magnetization at 4 points and during the trajectory in between. And the first task we had to reconstruct the descent phase and this bouncing trajectory. And that can be done partly by a magnetometer. Of course, we need external information. We knew from the OSIRIS camera in which direction we flown after the first touchdown. We knew from CONCERT where finally the landing site was. But we got a lot of information, additional information from the magnetometer as well. It's like if you have a small compass and if you're turning the compass, then you see that the needle is moving within the compass housing. And something similar like that, we try to reconstruct the motion of the lander. And of course, if you are bouncing to crater rim, as we see in the middle of this figure here, where we had this collision with a crater rim, then you see that this pattern changed dramatically, because if you're touching with one leg the crater rim, then of course the rotation period decreases and we are tumbling, and so you see another periods into the magnetometer signal. And we saw exactly the landing times because our sensor is mounted on a small boom, and if this boom is touching the ground a little bit, then you have a relative motion between boom and lander, and that generates a signal into the magnetic field data. So we know exactly the landing times, and we at least detected the multiplet touchdowns, which has finally presented by Stefan soon after landing. Okay, that's the trajectory reconstructed, and that at least the measurements we did during these trajectories. What you see on that figure is the magnetic field magnitude over the height to the surface, to the cometary surface. And that's not only the advantage that we are touching 4 points at the surface, we are touching we are measuring during the descent and during the ascent. So we have some statistical significance that we have to measure the same signature, which if it is caused by the surface magnetization during descent as well as during ascent. And we had the second advantage that we have during all the times the orbiter in space, so that all the external field variation, which has been somehow cancelled out, can be measured in parallel by the orbiter. So we have an accuracy for that measurement which never has been achieved before. If you see now this figure here, we see more or less nothing which can be really related to the comet. It's for all touchdowns and for the collisions the same result, and therefore with the information that most of the variation which was seen in the figure before is driven by the solar wind interaction with the comet, we can estimate that the field we measured, which causes by the surface, is less than, let's say, 2 nanotesla. That's a very conservative assumption. At that figure, you can see again this nice configuration with this orbiter magnetometer, RPC MAG, and the magnetometer on the lander. And here you see both signals, which are more or less identical. They have a high correlation factor. And that's the way how to remove the external field variation from the signature, which achieves this nice precision. And finally, we try to model the magnetization because on the left-hand side you see the picture for the ascent and for the descent, and we added to our measurement results a theoretical model of the magnetization we assumed as an upper threshold. And you see that nothing has to do with the field which we really have measured. Therefore, we could determine an upper threshold for the magnetization, which was in the order of 3 × 10⁻⁵ ampere square meter per kilogram. It's normalized to the mass. So that all together allows that we can compare this value with the values we know from meteorites or from lunar material, and we saw that those magnetization is much less. And we know, of course, that our spatial resolution is limited by the distance between our sensor and the surface. Therefore, we can only say something about magnetization for scales of 1 meter or larger. So we can say nothing about millimeter or centimeter scaled particles. But for these larger particles, we can exclude that magnetic forces have really played a role in the accumulation of the planetary building blocks. That was finally the result, and which, of course, limits the options for the planetary building. So one of these theories can be, at least for the higher scales, cancelled out.
Okay, Karl-Heinz Glasmayer, Technical University of Braunschweig, and I'm the PI of the Orbital magnetometer. And as Uli already mentioned, we are in a very lucky situation, not only that we had 3 surface contacts and have been able to fly over the surface, but also we had the orbiter as a monitor out there in space, some 17 kilometers from the surface. And what you see on this figure here is what we call the singing comet. Since August last year, we see a very clear signal in the orbiter magnetometer data. The frequency is about 50 millihertz, and this is a dominant signal in the inner coma of the comet. It's a clearly signal which is generated by the interaction of the comet, the outgassing comet, with the solar wind. And we are lucky in that this very unique signal is kind of a guide field. And doing measurements also on the surface, we also see this singing comet phenomenon. So it's not only present out there in the plasma, it can also be seen at the surface. So all the signal we see at the surface is dominated by this periodic oscillations. So we have kind of a very nice basis and background signal, and we can say that what we see on the surface is mainly due to this plasma phenomenon. It's not due to some mechanism, to some dynamical feature we see at the surface. For example, you could imagine if we fly over the surface and if we have a spatially varying magnetization, we would expect also time variations of the magnetic field seen in the lander, but we can exclude that because we have this guide field in the back. Maybe you go to the next. And just to demonstrate how clearly correlated these signatures are, you see registrations from both the orbiter and the lander. The green line is the orbiter magnetometer measurement, and the red line is the lander magnetometer, and you see almost no difference. So what's out there in space is also seen at the surface, and this significantly helps us to say that the magnetic field at the surface, as measured by ROMAP, is mainly due to the plasma physical processes seen in the plasma out there. I think without the orbiter data and this unique combination of both magnetometers, we would not have been able to discriminate between spatial and temporal variations. Next view graph. I think there's another aspect which is very helpful because we know what the signal is out there in space, and because we know that the same signal is seen on the surface, we can use both magnetometer measurements to orient the lander. You know, for the orbiter, we know how the attitude of the orbiter is, but we do not know that for the lander. Is it in this direction or that direction or that direction? Now what we do is, because we know that both are seeing the same signal, we just rotate the lander coordinate system in such a way that the measurements coincide with that of the orbiter, and that gives us an opportunity and a possibility to determine the attitude of the lander. So we know all the way down to the surface and at the surface, by the combination of both magnetometers, we now know the attitude of the lander. That's very important also for later attempts to find the lander and so on. Takes the next picture. Well, this is a little bit complex picture, and it's reflecting the complex plasma physical processes generating this singing. What you see here is we have outgassing from the comet, and the outgassing neutrals are ionized, and these ionized electrons and ions here shown by the yellow point and the brighter red point, they constitute a very strong current in this plasma. The current has a strength of about 100 amperes, And this current is flowing across the solar wind stream and the interplanetary magnetic field, and it's becoming unstable. This is like your garden hose. If you turn on the water, which is a current, you see that the garden hose is also moving around. And a similar thing is happening here. And this is generating this singing, which we are using as a reference signal to interpret also the lander observations. And this signal, as I said, was very important to really confirm that the field we see at the ground, at the surface, is below 2 nanotesla. Just to give you an idea what 2 nanotesla means, in this room we have something like 50,000 nanotesla magnetic field generated by processes within the Earth, and down at the surface of the comet we have something less than 2 nanotesla. So it's a very sensitive measurement we had to make there, and this was only possible by combining the two magnetometers. Next view graph. This is a very important thing I like to know. You can see I'm in cometary physics in Rosetta since 25 years. I started as a young person and have grown up, and I'm most fascinated by all the young people involved in the project and by all the cooperation which is going on. I think Rosetta is not only a nice combination of different instruments, it's also quite remarkable, truly international achievement. It's really fun to cooperate with all the different teams, young people, older people. We are all fascinated, and we go ahead with all this nice results coming up in the next months. Thanks.
Okay, so I'm Stefan Ulametz from German Aerospace Center DLR in Cologne. I'm the project manager of the lander. And I will give you some news on the status of the lander itself, on the status how we try to find it with observations from the Orbital instruments and cameras, and the status on the attempts for re-establishing contact. As you know, we are all hoping that Philae will wake up again when we are closer to the sun and we can do more science. As mentioned by Uli, we were obviously bouncing after the first touchdown at the comet. What you see right here is the trajectory as it was calculated using various data, images from the orbiter camera where the lander could be seen, also other measurements including the magnetometer, which helped a lot in determining the exact times and positions of these touchdowns. So what you see here, the red dot was where we were aiming for. Lander was touching down very accurately at the targeted point, but then it bounced off, had another contact, what you see a bit to the right at this crater rim, which deviated the trajectory, and is now somewhere in the area where this blue curve ends. And I say somewhere, we have quite a good understanding where this is. It's in the range of 30 times 50 meters or so. It's not really a huge area. It's not that we are completely ignorant where the lander is. But of course, we could not identify it clearly on any of the OSIRIS images yet. If you go to the next slide. This is an image you almost certainly have seen, taken by the Shiva camera on board the lander. And this is the surrounding of the lander, or one view as an astronaut would see it looking out of the lander, the terrain around. You see these various structures, and you also see in the front one of the landing feet of the lander. Now this is the image from the full panorama, which is best illuminated. The other images clearly show that we are surrounded by walls, and this is also the reason why the lander is in a very dark and poorly illuminated spot right now. Next view graph. This is just to remind you on the effort which is taken right now to find out where the lander is and to recalculate this trajectory which I just showed you in the view graph before. So obviously we have images from OSIRIS, but we were using the CONSERT data, that's the radar instrument which has been used for ranging, and this is also the instrument which was used to give us the exact position, exact in the range of this few tens times tens meters where we know the lander is right now. There was other data used, ROMAP, as I said, but also thermal mapper of MUPUS, the data from ROLIS, the down-looking camera. SESAM is an instrument which had acoustic sensors in the feet, so we could detect the touchdown very accurately and also learn something on the surface properties with this instrument. Okay, so next slide. Now this is an OSIRIS image, and what you see in this red ellipse, this is the range where the lander is expected. And if you hit again the button, we zoom in a little bit better, and you see there is plenty of little white dots. And just to remind you on the best images we have after the landing with the correct illumination, they were taken in December from an altitude of about 20 kilometers. The lander would be in the range of 2x3 or 3x3 pixel, and this exactly is the problem. It's not very distinct. We have to assume that there is some shadowing effect on the lander which camouflages it. And yeah, I mean, the later the evening, the more wine you drink, the more landers you're able to identify in this terrain. And this is also the reason why so far we do have candidates, but we could not really identify the exact location of the lander yet. Yeah, so next slide, please. Using the magnetometer data, and Uli was saying it's something like a compass, so it's a three-dimensional compass, we do know the attitude of the lander. So this is, the red dot is about the area where the lander is, and you see here a bit symbolic the lander, and this is quite accurately the attitude where it is. Yeah? Okay, next slide, or just hit it and it zooms in a little. Oh, well. So, some puzzles we are working on right at the moment. We have images from the descending lander, and we try to combine those images and the area we have, and we see where the first touchdown was, and try to combine this with measurements, with the acoustic sensors, with others. And this is not all exactly straightforward right now, so we need some more time to understand what does it mean. Did the feet really hit the rock? Did it hit soft material? This is one of the puzzles we have right there. The other thing you saw on the chart, that we were bouncing not as you would expect perpendicular away, but we were bouncing in a very flat way, which was good for ROMAP because they somehow could measure the magnetic properties over the surface. But that's not trivial, and it's an indication of some subsurface material, subsurface slopes. So also this is something we are working right now to better understand right there. Another thing is you have seen, and it was on the web, the imprints of the touchdown. They do not perfectly fit to the landing gear. Also something we are still working on. Is the lander laying on its side? You've seen the attitude, but since we do not have the high-resolution images and the lander not identified, we do not really know how is this relative to the immediate surrounding. These are puzzles. These are things we are currently working, and we still need to do further work to perfectly understand this. Yeah. Next slide. What is the situation right now? So the lander is resting on the surface. There is no way it would be blown away. Sometimes people ask me whether this is a danger. This is not a danger. It's resting there. It's not anchored though. We know in principle RF radio frequency communications is possible, but we also know we are in a place which is shadowed, very limited sun illumination. In the time in November we only had about 1 hour 20 illumination out of the cometary day, and this is also the reason why the lander went into hibernation. So we are sitting somewhere behind a wall or in a hole, and this needs to be better understood. Yeah, next slide. This is a curve from the days around November when we got housekeeping data. And what you see in red, in green, in blue, this is the, in this case, voltage output from the solar panels on the lander. And you see even one panel which was best illuminated. The red one only had sunlight for about 1 hour and 20, and the other two panels, one the side panel next to it, the other one the lid, they even got illumination for a shorter period, and this is the problem we have. Nevertheless, the comet, like the lander, are getting closer and closer to the sun every day, so the situation improves, and that's why we are hoping that at some point in the next weeks there will be sufficient power for the lander to wake up again and re-establish contact with the orbiter. Next slide. There's two basic requirements which need to be fulfilled to wake up. One is a temperature requirement, so the lander may not be too cold. It's somewhere in the range of minus 45 degrees. And we need power to not just boot the computer, but also to re-establish the RF, the radio link with the orbiter. When Philae would boot, because there is both these requirements fulfilled, every 35 minutes it would try to get contact with the orbiter, and since we switch on the orbiter communications unit, so after wake up within about half an hour, so we would be able to re-establish the contact once the lander is woken up. Yeah, next slide. We had a first campaign in March from 12th to 18th, when the geometry was good in terms of orbiter position above the lander and illumination. We knew this was very, very early, still in the year, still a bit too far away from the sun, and unfortunately, since we were too far from the sun, no lander signal eventually was received. Now, the day before yesterday, on the 12th, we switched on again the communications unit on the orbiter. At the moment, the orbiter is in a listening mode again, so we are hoping to get a signal, but yesterday and today, so far, we did not hear anything on this. Yeah. Next slide. This is now a three-dimensional kind of a cut model of the terrain based on the Shiva images and the Rollis images, so the panorama camera and the down-looking camera. Everything what you see bluish here, it could be determined from these images. What's gray is simply out of the field of these cameras, so we do not know whether there is also a wall or maybe some more open area where we may expect sunlight, and that's why it's difficult to predict exactly the solar input as the season changes on the comet, and it's also difficult to predict the internal temperatures, since of course they are very much dependent on the surrounding material. But this is what you see in blue here. This is about the surrounding, the immediate surrounding of the lander as based, as derived from the images of the lander. Yeah, the next one. Now, since we know the attitude due to the ROMAP measurements, and we know the position of the comet relative to the sun, we also can derive what's the solar path for these 1.5 hours when the sun is shining. And you see the red areas. This is the situation as it was end of last year. And unfortunately, the solar angle, the solar path gets flatter and flatter later in the year. So you see the green one is now about now, the April situation. And if we wait later, the sun goes flatter and flatter, which is good from a power point of view, because the side panels would be nicely illuminated, but it's not so good from a thermal point of view, because the lid where there is thermal absorbers will be less illuminated. Next slide. This is the prediction of the power we get, and you see the various curves. So the reddish ones were in January and March, very low, and now we are somewhere between red and orange. So the power on the solar panels should be sufficient to boot the lander in the coming weeks. The temperature we have to find out. Both requirements have to be fulfilled so the computer can boot. Yeah, next slide. So what's the situation? And this is my final slide now. As I said, we are at a location with very limited illumination. The situation is improving every day since we are approaching the sun. It's improving until perihelion on 13th of August. We, of course, do not have any danger of overheating. This was an original concern before we separated. But we are very cold, and this is a problem. So still, the situation is, and I've communicated this before, that there is a chance to boot probably in the April-May timeframe. If we also want to communicate, and of course we want to do this, it's May, June, the most realistic dates for Wakeup. And then if we get warmer and warmer, we hope that we will even be able to recharge the batteries. The detailed analyses are ongoing and continuing. This will be better once we would be able to identify the exact location on one of the images, because then we see the surrounding additional information as compared to the camera images we have from the lander. But we have to wait a little bit for this. So far, no contact with the lander, but as said, we get closer and closer, and we hope this will change, and I will have better news in a few weeks from now. Okay, thank you. I think that was my last slide. If you hit.
Thank you very much for the update. We'll now open the floor for questions. Is anyone here in the room?
Mariette Leroux from AFP. We've spoken on the phone before. I have a few questions about Philae, please. I would like to know how long it's going to remain in listening mode this time around. How long? And if this doesn't work again, when will the next attempt be? And the other question is, if you could please just explain to me the attitude. I'm sorry, I didn't quite understand from the slide.
Yeah, okay. So at the moment we have switched on the receiver units on the orbiter, and we may consider to simply keep it on, so stay in a listening mode. So whenever the lander is woken up and the geometry is in a way that there is RF link possible, we switch it. We will hear it immediately. Now, you know, there was these problems with the star trackers. Rosetta is now on a slightly different orbiter as originally planned. This is, by the way, not so bad for the lander, because we more or less stay now in the area where there is also sun illumination. So we may just stay in a listening mode and wait. The other point was regarding the attitude. And maybe you can browse back to the slide where this was shown. One more, I guess. Well, more than one back. Yeah. So you see it's a bit symbolic, this lander body and the three dots which symbolize the feet right there. Now this is the attitude relative to the comet, and we know it from the ROMAP measurement. So ROMAP is a compass, so we know this attitude. What we do not know is the exactly position where now exactly on the comet the lander is in this attitude. But we do know where the antenna pattern is showing. So in this sense it is useful, but it doesn't give us the real context of the rocks, the walls, the material around. Yeah?
The way that it's portrayed there is the feet in the air, is it?
No, that's just, it should be projected to the surface. It just shows you the attitude of the lander, and you could move it a little bit or project it somewhere where this red dot is. And of course the lander is very big here as compared to the comet.
Quirijn Schiermeier from Nature. Dr. Glausmeier, could you perhaps explain why scientists had thought that a body as small as that comet might have a magnetic field? I mean, I understand magnetic fields arise from the geodynamos in large objects like Earth or moons, but why should a relatively small object have a magnetic field?
Well, it's a good question. We know from the Earth that there are at least 3 contributions to the magnetic field we see and can measure at the Earth's surface. The major one comes from so-called dynamo processes in the outer core of the Earth, and we are pretty sure that such a process cannot happen in a small body like a comet. But at the Earth's surface, in the Earth's crust, we also know about magnetized regions where we have iron, little magnets which are oriented by the main magnetic field, or also have been put into orientation into what we now call remnant magnetization. We know that the Earth's magnetic field has changed over the past billion years. And if you take a lava flow with lots of iron or magnetized material in it, then because it's fluid and heated up, you can start to orient these little magnetized dust particles in such a lava flow. And if the lava flow cools, you are blocking and you are conserving the magnetization. This is what we call remnant magnetization. Remnant magnetization. And a similar process may happen in the early solar system. We know that comets also contain iron, and iron is one of these elements where you can expect magnetic properties. And there are also theoretical ideas that in the very early solar system, magnetic fields played a major role for transporting angular momentum within the forming planetary system. And these magnetic fields might then be able to orient the small dust particles now part of the comet. And if you have orientation of small magnetized dust particles into larger regimes, they should form also remnant magnetization. And this was the idea that we said, okay, we know there cannot be a dynamo operating, but we might have a chance to measure remnant magnetization. And if we would have measured remnant magnetization, it would give us information about the magnetic field strength in the early solar system. Now, the fact that we see such a very small magnetization of the cometary material, it also allows to enter this idea about the importance of the magnetic fields in the early solar system. And I think we have to restart the discussion in that direction again, because we feel that the fields have been much smaller in the early solar system than previously thought. Because if they would have been larger, then we most probably would have seen a more strong magnetization. And that is the scientific background and the interest we have in doing these measurements, but they need to be in a very decent and precise way.
I have a question. Two from online, but they're kind of similar. So I have Hamish Johnson from Physics World that was wondering if magnetic forces are not involved in the comet formation. You kind of answered this, but then how does that change the model for how comets were formed? And then Jacob Aaron from New Scientist was wondering if magnetic forces were not involved in the clumping together of planetary building blocks, then which forces were responsible?
It doesn't. It doesn't change the models, but it excludes one part of one of the models for the planetary formation. So if the magnetic forces are not able to align and at least to accumulate larger particles as we had it measured in the meter scale, we cannot say anything about centimeter scales. But for larger granulation like meter, we can be sure that at least if this comet is representative for the others, then there's no chance that you can have accretion with magnetic forces. So simply this magnetic accretion model for larger scales can be now excluded. That's the answer for what has changed for the models.
Thank you. Are there any more?
The question was more about what is the alternative explanation? What are the alternative explanations?
What are the alternative? Oh, there are some. So I'm probably not the expert for answering that question, but there are some alternative models. For instance, like if you have one lucky winner part, which is already a little bit larger than the other ones, and if this one will be collide with other smaller particles, then a little bit remains on this larger part, and these at least leads to a growing process for this only one. So the others will be destroyed at least, but this only one, larger one, can be grow up to higher dimension, up to meter and larger scales. And then, of course, if you are in the order of few tens of meters, then the gravitation becomes an important force for that. There's another theory. It's like a peloton at the Tour de France, for instance. If you're one leading guy and the others are in the shadow, you have similar situation in the gas drag in the preplanetary disk. So the other particles can be accelerate behind this leading part, and then of course relative velocity between this and the other parts becomes lower, and then again accretion could theoretically happen, and then van der Waals forces are still enough to keep all the things together. So that's maybe the two other models I know. Probably there are some others as well.
Jonathan Amos, BBC News. I mean, but at smaller scales than a meter. I mean, we see dust grains routinely in the galaxy, in the solar system, aligning with magnetic fields. So couldn't these processes begin on those scales? I mean, I'm talking on particle scales of dust, and then some of these other forces come into play at a later stage. Yeah?
We cannot exclude that for smaller scales, of course. It's still...
I think the scale we can do measurements on is about 1 meter, which is about the distance we have of the magnetometer, the room-up magnetometer to the surface. That is about the spatial scale. We can also say something about the magnetization. This does not exclude that on even smaller scales, millimeter or sub-millimeter scales, we have magnetized grains. And there are instruments on board Rosetta where we later might be able also to infer information about that magnetization. But on this critical scale of about 1 meter, which is an interesting scale because there we have lots of questions concerning their formation, we think we can exclude the importance of magnetic forces.
Right, because I mean, just going back to the science papers earlier in the year, there was a lot of talk about these goosebumps and this preferred scale on 67P, that these were the planetesimals, these were the fundamental building blocks of that scale, that sort of 1 to 3 meter size of objects that came together to form 67P. So I mean, are you thinking in that kind of arena?
Yeah, this is a spatial scale where we, as I said, we can, and there we can, we just think we can exclude the importance of magnetic forces.
And the meter scale is a very conservative assumption. So we calculated with a distance of the sensor of about 1 meter, but it could be much, much closer if we see the orientation of the lander here. And we know that maybe 1 feet will be not in the air, but has no contact with the comets, and we need a 3rd feet, and that 3rd feet could be, for instance, the boom of the roam-up instrument, which we have some other indication. In that case, we are very close in the centimeter, maybe in the 10 centimeter scale. But of course, we have to, for science paper, we have to assume conservative assumption, and therefore we limited our suggestion to 1 meter scales only.
So on the micrometer scale, there might be magnetized dust particles. But if you have many of them, you need a guide field to orient them, to align them to larger structures, meter size or so. And this is what I think we can exclude from our measurements. This does not mean that on the micrometer scale there is not magnetization. But therefore we need different observations.
Right, okay, and then I've got a couple of questions, one for Matt, one for Stefan. The one for Matt, I mean, is this it now until after perihelion? We can't go any much closer to the comet because Rosetta will just throw a fit.
Well, it doesn't throw a fit, it behaves itself. It's designed to do this. It's just, we are at about 100 kilometers, we're stepping closer, so we'll get to a point where we're trying to find how close we can get, basically, and that I couldn't give you an answer on what that number is at the moment. That's the situation we're in, is to step a bit closer and a bit closer week by week, and then see what the situation is. And then the transition to this terminator orbit as well will be interesting, because there may be particle dynamics involved in making more dust be there than on the day side, for instance. So we have to see what the environment is. It's really, in some sense, the whole orbiter now is an experiment. rather than the separate sub-instruments.
But in a sense, as you move towards perihelion, the police cordon must surely be moving.
Yeah,
out.
well, this is what we are thinking. But again, we have to wait until we've done a few of these legs to get a feel for again how the spacecraft is going to behave. But this could be one option is that we are a significant standoff distance. But I'll be discussing with the mission manager and also the people at ESOC what exactly we can do in case this is the situation. Basically, try as best we can to get the best science out, given the comet that we have and the spacecraft.
And then, Stefan, you mentioned the temperature. This minus 45 Celsius. Is that a flaw? I mean, if you go below that, that really causes problems for the onboard electronics.
Yeah, the lander is designed in a way that if it's below, the power input from the solar generator would be used for heating and not for booting the computer.
Right. So, I mean, do you have concerns about the temperature where it is?
Well, if the situation is bad, like if we also had some ceiling, which we do not know because we don't have a camera looking upwards, the shadowing effect may be bad. I mean, there is a large range of uncertainty, but if it's on the bad side of this uncertainty, it could well be that we stay cold, yeah.
And in the red ellipse images, what's the size of the red ellipse?
The red ellipse is larger than what we really believe. It's a bit symbolic. The red ellipse was something like 300 times 50 meters, but our belief is much better in terms of the localization. It's rather in the range of 30 times 50 meters or something like that.
Karl Orban for the Deutschlandfunk Germany. Just a quick addition to the previous question to Stefan Ulamet. So, what parts of Philae are most likely to still work when the lander got very, very cold, and which ones are more likely not to work anymore when it wakes up?
I think that's difficult to say which one would. The magnetometer would work perfectly. Now, of course, the most important part is that the power control system and the central computer, which is the brain of the lander, would work. There is no strong reason why they should not be working anymore if the power is sufficient and the temperature is sufficient, although in this period of hibernation we have faced, or the units have faced, temperatures below the qualification level. Yeah? So if the central computer, which is redundant, or at least one side, and the power control system and the communication system are working, then I would say the rest, including the instruments, should be working as well. One can never rule out that some instrument is not operational anymore because everything gets very cold, but in principle everything should work. That includes the mechanisms, like having another attempt of drilling.
I have another question. This is from Alexander Teleshev from RIA Novosti Newswire. In January, there was a paper about a thick layer of dust, that's 67P, will shed when it approaches the sun. Did it happen, and did the instruments of Rosetta detect any changes on the surface in terms of chemical or mineral composition, reflectivity, and so on?
We've started to see an evolution on the surface, but it's a very gradual one. So there are signs of maybe some of the subsurface showing through. So we have indications that we're seeing surface ice, and some of that was also detected by the lander when it landed, the fact that there was this very hard subsurface. It may be that we're seeing signs of that from the orbiter now on the global sense. But it matches very well with the level of emission of volatiles that we were observing from other measurements that feed the coma. The amount of the surface that you need to have that visible material matches up very well. So, and we're starting to see that with the increase in activity. So it appears to be that that's happening. But it's ongoing.
We have time for one or two more questions, if there are any more questions. We have quite a few from the chat, so if there are no more questions from here, I'll just...
So we have This is for German radio. What do you think will be the impact of the recently observed navigation glitches for Rosetta's science observations?
Well, in the near term, we've lost some of the close observations. One thing we were planning to do was a lot more of these close flybys, but at the moment they're deemed to be not possible. So we lose that aspect in the near term. And as I said before to the previous question, we are looking at what can be done to mitigate this. But we've come back online and we've started to make scientific observations at a limited sense that we have some pointing that we can't do. It'll become clearer in the next months exactly what we can do and what we can achieve in the near term. As was alluded to, we're going through perihelion, which is the most active, the time when we were expecting not to get that close to the comet in the first place. So this is compounding our situation.
And this is from Leo Enright from Irish TV. How big a concern are the temperatures that must be lower than expected at the final landing site? So what instruments are more at risk, and is the comms package very temperature sensitive?
Well, as I said before, none of the units within the so-called warm compartment of the lander was qualified for these low temperatures, but none of them is particularly sensitive. That includes also the communications unit. So a problem one may face with these low temperatures is some thermal stresses on the electronics boards, and they may damage soldering points. This is a danger we have to live with, but there is none of the instruments particularly more sensitive to these temperatures. All the instruments and mechanisms which are outside the warm compartment of the lander, like on the balcony or so, they are all qualified also for very low temperatures, because we were expecting those to get cold even if we had landed on the planned landing site.
Thank you very much for your time. I'm afraid we don't have time for more questions. The next press conference is in less than 10 minutes, is on the impact of geoengineering. Thank you. Thank you.